In this lesson about estimates and sample sizes, we're going to learn about estimating a population mean when the standard deviation sigma is not known. This section presents methods for using the sample mean to make an inference about the value of the corresponding population mean. Some key concepts that we will be studying in this lesson are: 1. We should know that the sample mean x bar is the best point estimate of the population mean mu. 2. We will learn how to use sample data to construct a confidence interval for estimating the value of a population mean. And we should know how to interpret such confidence intervals. 3. We should develop the ability to determine the sample size necessary to estimate a population mean. The requirements are that the procedure we use has a population that is normally distributed, or the sample size must be greater than 30. The margin of error used for the estimate of mu with sigma not known is E equals T sub A over 2 times S divided by the square root of n. T sub A over 2 is a critical value that we will be looking up in a different table. The table we will use is table A3. The T sub A over 2 also has n minus 1 degrees of freedom. So we will always subtract 1 from our total in the sample when we look this critical value up. This is called a student T-distribution. If the distribution of a population is essentially normal, then the distribution of T equals x bar minus mu divided by S over the square root of n. This is a student T-distribution for all samples of size n. It is often referred to as a T-distribution and is used to find critical values denoted by T sub A over 2. The number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. The degrees of freedom is often abbreviated df. Degrees of freedom is equal to n minus 1 for the methods in this section. Here's some notation that we'll be using. Mu is equal to the population mean. X bar is equal to the sample mean. Lowercase s is the sample standard deviation, and lowercase n is the number of sample values. Capital E is the margin of error, and T sub alpha over 2 is the critical T value separating an area of alpha over 2 in the right tail of the T distribution. This is our confidence interval formula that will help us estimate mu with sigma not known. It's x bar minus E is less than mu is less than x bar plus E. So if we compare this to the p-hat formula that we learned in the previous lesson, it's set up very similarly. The other one was p-hat minus E and then p-hat plus E. So notice we're still setting this up where we have our sample here, sample mean, and then we're adding and subtracting the margin of error from it. Now our notation in the middle is, since we're estimating a mean, then we have to use the correct notation for that. So you're going to put a mu symbol in the middle. Now the margin of error formula is T sub A over 2 times S over the square root of n. And it also is associated with the degrees of freedom of n minus 1. And we look up the critical value in table A3. So here's the general procedure that we'll use for constructing a confidence interval for mu. Verify that the requirements are satisfied where the sample has a normal distribution or it's a greater than 30 sample size. Using n minus 1 degrees of freedom, refer to table A3, or you can use a graphing calculator with technology to find the critical value T sub alpha over 2 that corresponds to the desired confidence level. Evaluate the margin of error E. Find the values of x bar minus E and x bar plus E. Substitute those values and set up your confidence interval. Round the resulting confidence interval limits. Here's an example. A common claim is that garlic lowers cholesterol levels. In a test of the effectiveness of garlic, 49 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after the treatment. So in this situation, 49 would be N. The changes in their levels of LDL cholesterol have a mean of 0.4 and a standard deviation of 21.0. So since these values come from the research and the sample, 0.4 would be my X-bar mean, and standard deviation here would be S, since it's sample standard deviation. Use the sample statistics of N equals 49, X-bar equals 0.4, and S equals 21.0 to construct a 95% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. What does the confidence interval suggest about the effectiveness of garlic in reducing LDL cholesterol? So, this 95% confidence interval, we have to be careful here because we are not using the critical value Z's that we did when we were setting up a confidence interval for a population proportion P. So that's going to go with the P. Here I have to use a T sub A over 2. So are the requirements satisfied? Let's check. It is a simple random sample, and our sample size is greater than 30, so we're good to go with that. 95% implies that alpha is 0.05. With N equals 49, the degrees of freedom is always one less than the total in your sample, so the degrees of freedom is 48. So let's go ahead and take a look at our table A3 together to see how to find the corresponding critical value for the student T distribution. Okay, so let's look at the student T distribution. So this is what it looks like, and you'll see that it has a column of degrees of freedom. So this kind of tells you what row you want to land on. So this is your one less than the total in your sample. So for this example, since we had 49 in our sample, we want to go to the 48th row. Now notice we don't have a row 48 here, so you're going to go to the closest. So we're going to go to row 50. So next, to find which T we're going to use, you have to look at your headings here. Notice we have area in one tail, area in two tails. So this comes from the normal distribution curve, where you're going to have your critical T, the negative and the positive. So it's just like the Z picture. And our confidence level was 95%. So we have 95% in the middle here, and so that gives us a leftover alpha of 5% in both tails. So alpha is 0.05. So we can go to area in two tails, 0.05, and that would be giving us the correct T. It's going to be in this third column. If you look above it, it's giving you area in one tail, and that's the same thing. So if we split up the 5%, you're going to have 0.025 or 2.5% in each tail individually. So this is the same thing. You can just do the two tails if you want to. Okay, so putting that together, so we're going to go down to row 50, and we're going to go to the third column over, and this is our critical T value that we're going to use for our margin of error formula. So let's go back to the PowerPoint and finish this example. So now that we have finished looking up our critical value T, we found that it was 2.009. So using that and using the other information, we have E equals critical value T times standard deviation over square root of N. So this should actually be an S for that notation. So we have 2.009 times 21 divided by square root of 49, and that gives us a margin of error of 6.027. So now let's construct the confidence interval. It's X bar minus E, and then we have X bar plus E. So we have 0 0.4 minus 6.027 gives us the lower value of negative 5.6, and 0 0.4 plus 6.027 gives us the upper value of 6.4. Notice we have mu in the middle because this is the estimate for the mean. Also notice I didn't round to 3 decimal places. We only have to do that for proportions. So when you have a mean, you can round to the nearest tenth if you'd like. So here's an interpretation of this answer. We are 95% confident that the limits of negative 5.6 and 6.4 actually do contain the value of mu, the mean of the changes in LDL cholesterol for the population. Because the confidence interval limits contain the value of 0, so notice that it goes from a negative to a positive, so it does overlap 0, it is possible that the mean of changes in LDL cholesterol could be 0. So this interval contains 0 on the number line. So that suggests that the garlic treatment may not have affected the LDL cholesterol levels at all. So it does not appear that the garlic treatment is effective in lowering LDL cholesterol. So here are some important properties of the student T distribution. The student T distribution is different for different sample sizes. So we'll show that on the next slide for when we go from a sample of 3 to a sample of 12 and how that affects our student T distribution. Also, the student T distribution has the same general symmetric bell shape as the standard normal distribution, but it reflects the greater variability with wider distributions that is expected to occur when you have small samples. The student T distribution has a mean of T equals 0, just as the standard normal distribution does. The standard deviation of the student T distribution varies with the sample size and is greater than 1, unlike the standard normal distribution, which has sigma equals 1. As the sample size n gets larger, the student T distribution gets closer to the normal distribution. So this is showing student T distributions for a sample size n equals 3 and a sample size n equals 12, and it's also plotted with the standard normal distribution, which is in blue. As we increase our sample size from 3 to 12, we'll see that it more closely approaches the normal distribution. So increasing sample size is better because it does approach that normal distribution curve. If we have a confidence interval set up, we can estimate and figure out what the sample mean was and the margin of error was, just like we did when we had the confidence interval for a population proportion. So to find out what x bar is, you're going to add up your upper limit and lower limit and divide by 2, and the margin of error is E equals upper limit minus lower limit divided by 2. So here we're going to use the given confidence level and sample data to set up a confidence interval for the population mean mu. We're told to assume that the population has a normal distribution, so it satisfies the requirements. So the lifespan of a desktop PC, we want to estimate what the lifespan should be. We want to set up a confidence interval to do that. We want to have a 99% level of confidence, and we have a sample with 21 desktop PCs, and in that sample the mean lifespan was 6.8 years and the standard deviation was 2.4 years. Note that sigma, the population standard deviation, is not known. We just have our sample. So we are told that the population is normal, so we're going to use student T distribution. So the confidence interval is x bar plus or minus margin of error, or it's x bar minus E is less than mu is less than x bar plus margin of error, where the margin of error is critical value T times standard deviation divided by square root of n. So you can actually put the critical value in the numerator of this little formula here, multiply it by standard deviation and divide by square root of n. So x bar is the sample mean, that's 6.8, and the margin of error is 2.845 times 2.4 divided by square root of 21. So let's backtrack and figure out where this 2.845 came from. that is our critical value T. Remember, we do not use table A2, it's not a Z. And so we're using table A3, and we need to know degrees of freedom. Degrees of freedom is n minus 1, so if there's 21 in my sample, I'm going to go to the 20th row of table A3. Now my confidence level is 99%, so alpha is going to be the leftover area, which is 1% in both of the tails. So let's take a look at table A3. So in table A3, we want to first go to the appropriate row. In this example, we had 21 desktop PCs, so my row that I want to go to is the 20th row. Also, my confidence level was 99%, so alpha is 1% or 0.01 in two tails, or it's 0.005 in one tail individually. So I'm in that first column. So my critical value T is in the first column on the 20th row, 2.845. So now let's go ahead and proceed. The margin of error, when we calculate from the formula here, we're going to get the margin of error is about 1.490. And so I want to do x bar plus the margin of error to get the upper limit and x bar minus the margin of error to get the lower limit. Make sure you use a mu symbol for your confidence interval. So the mean desktop PC lifespan we would assume to be ranging from 5.31 years to 8.29 years. The world's smallest mammal is the bumblebee bat, also known as the Kitti's hog-nosed bat. Such bats are roughly the size of a bumblebee. Listed below are the weights in grams from a sample of these bats. Construct a 95% confidence interval estimate of their mean weight. Are the confidence interval limits very different from the limits of 1.56 and 1.87 that are found when assuming that sigma is known to be 0.30 grams? So this right here is just a follow-up question. We can't use it for the initial part of the problem. We're asked to construct a 95% confidence interval estimate, and here's a key word, mean. So when you take this exam, you're going to have to determine which appropriate formulas to use, and it's all based on if you're doing it for a proportion or for a mean. So if it's for a mean, then you're doing the x bar formula. And this is the format for that. Okay, and then you look at what's E. So E is defined as being the critical value T from the student T distribution times S divided by square root of N. So I need to know T, and that comes from the 95%, and I got to look it up in table A2, or sorry, A3. S is the sample standard deviation, and then square root of n is the total, or n is the total in my sample. So let's look at the values that are given to us. Now this is the raw data, and we do not know from this yet what the standard deviation is. We don't know what x bar is. So we can calculate that in our calculators just like we did in an earlier chapter. So do not use any handwritten formulas to find the standard deviation. Just type the data into your calculator. So if you're using the TI30X2S calculator, you will need to clear your data. So you're going to press the data button, but you're going to go above it, and you're going to do second data. And you're going to arrow over to clear data. You're going to underline that and then press equals. The second step is to go back and repeat that. So do second data, and you want to make sure that you're set up for one var statistics. So underline that and press equals. Now your calculator should say stat on the main screen. Once you've set it up in stat mode and you've cleared your data, you can enter in these values. So now just press data, so don't do second data, and it will say X1. So type 1.7 and then press the down arrow button. Then it says frequency. Frequency is set to be at 1. You can change it, like if you did not want to type in all of these 1.7s, you could change the frequency to 2. You have to be careful though to make sure that you cross it off of your list. I just like to keep it at 1 and just type the numbers in. So you want to arrow past frequency 1 and then you want to go to X2 and you're going to type in 1.6, arrow down, and keep doing this until you've entered in all of your data. Now other calculators might have you type the data into a list, so it just depends on the model of calculator you're working with. So if you need instructions, you can Google your calculator model, or you can look at your user's manual and focus on the section about statistics. So once you've entered all the data in on this particular calculator, you're going to have a button next to data that says Stat Var. Stat Var is your calculate button, so press it and you will find what N is, and you will find X bar, and you will find SX. That is your sample standard deviation. Okay, so type the data in your calculator, and this is just going through those steps that I did on the previous slide, so you can reference that on your own. But we will get that the standard deviation, the X bar is 1.713. So notice I'm not rounding it to the nearest tenth. I'm keeping about 3 decimal places for that. So we have X bar is 1.713, and what's S? That's a standard deviation of the sample, and so from the calculator it's SX and it's 0.259. Again, go out to 3 or 4 decimal places in rounding. N is the total in the sample, so we had 15 numbers, so N is 15. Then we have to find T. Okay, so that's going to be associated first with the degrees of freedom. The degrees of freedom is 1 less than the total in our sample, so we're going to have 14 for the degrees of freedom. So on table A3, we're going to go to the 14th row. We're told to use a confidence level of 95%. So the area left over in 2 tails is 0.05. So we will go to the appropriate column that has an alpha of 0.05 in 2 tails. You could also use the 0.025 in 1 tail, which is listed above it. And we're going to go to the 14th row. And this will give us T is 2.145. So the margin of error formula is critical value T, 2.145, times S, which is 0.259, divided by the square root of N, so square root of 15. So the margin of error is 0.143. To set up the confidence interval, we're going to do X bar minus the margin of error and X bar plus the margin of error. So that gives us the limits of 1.57 and 1.86 when we use X bar of 1.713. Make sure you have mu in your confidence interval, and you can also label it if you want to. So the mean weight of these bats in grams would range from 1.57 grams to 1.86 grams. We were asked if these confidence interval limits are different from the limits that were achieved from a standard deviation sigma for the whole population known to be 0.30 grams. And when they set that up, they got these limits of 1.56 and 1.87. Now these are very similar to what we got, so no, the limits are nearly the same when we set the confidence interval up using student T-distribution. So now let's focus on how to set up and find a sample size required for estimating a population mean. So the notation we'll see is mu is equal to population mean, sigma is population standard deviation, X bar is sample mean, and E is desired margin of error. Z is the z-score separating an area of alpha over 2 in the right tail of the standard normal distribution. If the computed sample size n is not a whole number, round the value of n up to the next larger whole number. So assume that we want to estimate the mean IQ score for the population of statistics students. How many statistics students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? So in this, we're told that we want 95% confidence and the sample mean is within 3 points. So notice that we're using the exact number 3 for the margin of error. We're not converting it at all. And we are also told that the standard deviation is 15 points for the IQ test. So the sample size n is equal to 1.96 times 15 divided by 3, and we're going to square that result. So we get 96.04 when we type that in the calculator, and then we're going to round that to 97. The Tyco Video Game Corporation finds that it is losing income because of slugs used in its video games. The machines must be adjusted to accept coins only if they fall within set limits. In order to set those limits, the mean weight of quarters in circulation must be estimated. A sample of quarters will be weighed in order to determine the mean. So how many quarters must be randomly selected and weighed if we want to be 99% confident that the sample mean is within 0.025 grams of the true population mean for all quarters? Based on results from a sample of quarters, we can estimate the population standard deviation as 0.068 grams. So in this problem, we're told the margin of error is 0.025, sigma is 0.068, so then we're going to use a z, a critical value z, and this is because this sigma is known here. So it's 2.575 for 99% confidence. So the sample size formula that we use is n equals critical value z times sigma divided by margin of error, and then we square that result. So that gives us 2.575 times 0.068 divided by 0.025 quantity squared. This gives us 49.056, and we always round n up to the next whole number, so we need to get at least 50 quarters in our sample.